Okay, it's time to start. So it is a pleasure to introduce Jay Young from Washington University that today will talk about resolution from stratification and lattices.
Thank you for the introduction. And this is I'll cover a bunch of stuff, but this is the actual results from me are going to be with joint work with Christine Burkesh, Lauren Crinton Heller, and Greg Smith. But we'll start with just lattice ideals. So, right. So for a lattice, so let L inside of Zn, a lattice. Right, then we define our lattice ideal as x sub L is the ideal generated by all binomials of the form x to the a plus minus x to the a minus a for a in L, where, oops, wrong symbol, where a equals a plus minus a minus and a plus and a minus non-negative. Right. And here with the L is in Z to the N, so that non-negativity, that makes sense. Right, and these are the common object of study. This lives in, I should really say this lives in the polynomial ring in N variables. Right. And in particular, these are prime binomial ideals. In fact, these are exactly the prime binomial ideals. So these are also the toric ideals. That will be important as we go along. And the point here is that we're going to start by asking, how do we resolve? So the question, can we give resolutions? I should give this ring a name. Let's call that S. Every ring today will be S, essentially. It'll just be a different ring every time I write S, unfortunately. I don't want to have 5 different ring names, but they're all going to be polynomial rings, so it'll be fine. It'll just be different polynomial rings. Can we give resolutions of S mod I L, right? Okay. So in some sense, Bayer Sturmfeld's in the cellular resolutions paper gave a partial an answer to this, at least a combinatorial tool to let us try to construct these resolutions. So let's say Bayer Sturmfeld's, that's not how you spell it. 98. I'm always gonna look. Sturmfeld's. Yes. At least I didn't add the D by accident. But, so this is cellular resolutions. And usually when you see cellular resolutions, especially so the first time you see cellular resolutions, it's for monomial ideals and rather than binomial ideals. So you might ask, how do we actually do this? And we'll get there. But first, let's do cellular resolutions in monomial case, because we'll build off of that, and that'll give us the binomial case. So cellular resolutions. Of monomial ideals. Monomial, I'm going to say ideals. The parentheses around ideals will make sense later. Monomial ideals, maybe I should just say ideals slash modules. Let's say ideals slash modules. Whatever I mean by that. And so the canonical example, and it's best just to illustrate this with an example, because defining it carefully takes a little bit of effort, is if I take the ideal x, y, z inside of, whoops, that's not inside, k adjoin x comma y comma z, right? And then I want to resolve this, and I draw this picture where I have a triangle. I need to make the triangle bigger than that. That's not going to fit. is x, y, z, and you label, it's enough actually to label the vertices. The rest of the information is sort of induced from this. You can take LCMs, and we'll get xy, xz, and yz, and this middle will be xyz. Of course, there's only one sort of plausible, simple, and easy resolution of this ideal, which is the Zero complex. So you get this S1, S minus 1 to the third power, not plus, what am I writing? S minus 2 to the third power, X minus 1, no, not 1, 3 to the first power. So this is our resolution. This is a free resolution. Free resolution. In fact, it's minimal of S mod. Oh, I said S, but I didn't tell you what S was. Let's say, okay, join X, comma Y, comma Z, mod the ideal that I wrote down up here. Okay, let me make sure I'm not going insanely fast, because that's what I tend to do. This is straightforward enough. The end idea is that this is the S, which if you're used to simpliciter complexes, this is secretly for the zero simplex, the empty simplex. But either way, it's there, and it will disappear later when we're doing the module stuff. These are the copies of Z. So this, sorry, not copies of Z. These are the vertices. These are the vertices. Right. So this map will be well, it's essentially the labels on the vertices. So it'll be in some order X, Y, Z. These are the edges. Right. So we have to be a little bit careful, and hopefully I'll get this the right way around. But up to some labeling, and this is where I'm just going to confuse myself. That's why I'm confused. This is drawn the wrong way around. Right. I'm like trying to multiply these matrices and they make no sense. Negative y x 0, negative z 0 x 0 negative z y, something like this. And I'm not going to bother with that. It's straightforward enough. But this is the single face. And so the shifts are from the monomial labels, and the maps are from the divisibility, the division between the labels, right? This maps to this by y, and this maps to this by x, up to choosing signs. This is the cellular resolutions of monomial ideals. There's a lot of this you can do. There's interesting questions here just by in and of itself, because it's actually sort of annoying to figure out in general. When you have minimal cellular resolutions of a monomial ideal, for instance. But that's not what we're actually going to worry about. We want to resolve a toric ideal. So for cellular resolutions of, let's say, toric ideals, or lattice ideals. Let's say lattice ideals, that's what they would have said. Well, we want to replicate some of this. The naive thing would be to try to like replace the labels by binomials and hope that things work. Doesn't work. But what you do instead is you resolve a related. So this is really due to Bayer. This is also due to Bayer-Stimfeld. So let me just put it again. Instead, resolve. Well, this I should tell you what my. No, I have the ideal up there. Okay, resolve M sub L, where this is going to be some. So it's going to be S times the elements of the form x to the a for a in L, right? These aren't monomials, they're Laurent monomials, so this will live inside of the Laurent polynomial ring, which I'm just going to denote by K adjoin C to the N. But this is now going to be a sub S module of the Laurent polynomial ring viewed as a S module. This thing is obviously infinite in some sense. It's infinitely generated. But it is actually very nice in that it's very symmetric, because if there's this symmetry of adding elements of multiplying by elements of L, or adding elements of L, if you want to think about it as addition of exponent vectors. So it's not actually as infinite as it looks. It's actually very controllable and very tame. But we'd like to resolve these things. And how do I resolve these? Using cellular resolutions. Okay, that'll give you some, well, finite length, but infinite in rank, free resolution of this module. And then quotient, put this in quotes for now, by the L action to get a resolution of S mod IL. So the point will be that under this quotient by the L action, which is a little annoying to write down, so I don't want to worry about it, ML will become S mod IL. And so in this way, your module that you resolved at least becomes the module that you want to resolve. And you have to worry about, did I mess up the resolution? Is it still a resolution after I do that? Or did it become, some arbitrary complex? And this is what Bayer-Sundfeld did. They verified, yes, this quotient by L operation, which they phrase as a tensor, does in fact preserve the complex, does in fact give you a resolution if you start with a resolution. Okay. So that's a little abstract. I want to do this in one concrete case. For which I will actually cite another result. So this is sort of the beginning point of actual theorems written down. This is not my theorem. So I'm going to cite a theorem of Bayer, Popescu, this is 2001. And so what I want to say is there are general techniques to construct cellular resolutions for things constructed with monomials, and you can apply those techniques to ML and just hope that it gives something small. And sometimes this works, and sometimes you're just lucky and it just works. And so that's actually what Bayer-Sundfeld do in the original paper. Is they say, well, they don't describe it in excruciating detail, but they say, well, if you want some resolution, you could just take the whole complex. And at least that'll be some resolution, and you'll be able to talk about that resolution. It's not too bad. Professor Sundfeld says that in one specific case, we can do much better. We can give a very concrete resolution. And in fact, we'll know this resolution is minimal, but I'm not going to talk about the minimality right this moment. So let L in Zn be a unimodular lattice. I'm not going to work too much about unimodular right this moment, but the minor should be plus or minus 1 or 0. Okay, so this will be J sub L will be the ideal generated by this thing. Well, you would just have X's, but now we have Y's as well. Inside of the appropriate polynomial ring for A, inside of L, wrong symbol, same plus or minus notation as before, and this is an ideal inside of K adjoin a bunch of X's and K adjoin a bunch of Y's. So now we have the setup. Then there exists a cellular resolution of S mod JL of length, dimension of L, or rank of L if you want to be pedantic and say it's a group. So let's talk about this a little bit. There's one remark I want to make. This is not how we define lattice ideal. This is not the lattice ideal of L, but it is the lattice ideal of something. No, so J sub L is actually I sub L for something that's sometimes called lambda L, the Lorentz lift of L, where lambda L, well, now this is in Z to the 2n, is all pairs of vectors v comma minus v for v in L. So this is still a lattice ideal, so we can still use the same tools, but also these are isomorphic as, well, abelian groups, i.e. lattices, but I'm going to be very specific and actually say abelian groups here. But they're isomorphic. Of course, they're embedded in different places. Okay. I really wish I had a clock at the back of the room instead of having to look down at my watch every time. I guess that's true. There is a clock on the screen. I can look at that. Okay. Yes.
What kinds of lengths would you expect?
That's a good question. This is as good as you can expect. This is codimension. So L is the dimension of L is the codimension of this ideal. In fact, though this is reasonably natural because naively speaking, you might think, oh, I just take generators from a basis. That's not actually going to work, but naively it's close enough. And so you should expect dimension L many generators. So this should be the codimension. So the codimension is the best you can achieve because, well, the resolution, free resolutions always have to be length at least the codimension. So this is best as possible. If you did the whole complex, it depends on how complicated your ML is. But I don't know if there's a theorem that says it's still as best as possible, because in general, S mod IL is not going to be Cohen-Macaulay. So you don't always get this in general. And this will be part of the point of today's talk is getting something like this in general. But you shouldn't expect the generic constructions of cellular resolutions of monomial modules ideals to give you the best resolution always. And in general, they're certainly not going to give you the minimal resolution unless you're lucky. Yeah. So are they toric? I mean, are they prime? I don't think they're prime in general, right? So if they're prime binomial, then you are a lattice ideal. So you can ask the question there for those. But if you're not prime binomial, then this stuff doesn't quite work. I do have some questions about sort of exactly what you can do even if you're not prime. You can get a surprising amount of stuff to still work, but you lose the niceness of lattices, at least a little bit. Other questions? So let me draw a picture of what this looks like. So in this case, my lattice is going to be, I'm going to actually present it as equations because it's simpler for this one to present it as equations. 3 A plus B plus C equals C. My lattice, and my ideal, J L, going to be the ideal segment 5. In general, worried about whether this is enough. That's 1. X0 minus y1, y0, sorry, x0, y1 minus y0, x1, and x1, y2 minus x2, y1. Not being silly, right? Yeah. So this idea inside of For reasons I want to zero index here. There's our. And then I'm going to draw a picture. I'm going to draw a picture of a cellular resolution. The cellular resolution is actually going to be infinite, but you'll notice again, there's sort of this L equivariant structure to all of this. So we can replicate some finite thing by translation by L, and it'll give us the right picture. So let's draw this picture. It's going to take me a sec. I need to make this bigger. Edge here, whoops, missed. So this is our cell complex. It continues off forever, but non-terminated bits are supposed to represent, but this is one square of it. So this is one square of the lattice, and you just replicate this. What I'm going to do is I'm going to label this point by 1. I'm going to label this point by x0, y2 over x2, y0. This point will get a label of x1, y2 squared over, that does not look right. Why is that a squared? Oh, that's fine. One of the things, x0, x1, y2 squared over x2 squared, y0, y1. And then this point will get a label of x1, y1 over, no, that's a y2, sorry, y2 over x2, y1. Okay. And then the remaining labels are by LCMs. You do have to be a little bit careful about what I mean by LCMs. I mean LCMs as Laurent monomials viewed by under multiplication by S, by positive terms. For instance, the LCM of these two is x0, y2, not this term, because this has higher powers of x2 and y0. Just have to be careful not to get confused. Okay. So how did I actually construct this? Well, broadly speaking, so this will give me a resolution. Let me write down the resolution. This will give me a resolution, and this resolution will be S. Okay. Spaced right. Okay. So this might look a little weird. Let me tell you how I get this complex from this resolution from this data. These are actually the vertices now. These are the edges. And these are the two cells, the simplices. Let's say just two, let's just say two cells. So I claim there's one vertex there. Why is there one vertex there? Because this is, so that the lattice, these are lattice points. So this whole picture lives inside of sort of RL. This R, what I mean by this is, well, it's literally R times L, but you can also think of it as L tensor R, depending on how you want to think about it. This picture lives in RL, and these are the lattice points. These vertices here are the lattice points. So we have in this picture, lattice points. And I was when we quotient out LX, these vertices are identical. And in fact, X cells you quotient by the symmetry. And so you get solution. And in general, you do something like procedure. think of as living inside of R to the n. Right? So we have L lives inside of Z to the n, or in this case, Z to the 3. So RL lives inside of R to the n with coordinate hyperplanes. Well, hyperplanes, or not just coordinate, but parallel to the axes, parallel to the coordinate axis. Basically, this is the grid structure.
Can you restore the sound, please?
Okay, I'll try to continue. But we intersect with the sort of the grid, in Rn, the standard grid. And then this gives us, take the CW complex. And label vertices by, well, okay, so here's where the cleverness is. By the corresponding monomial x to the v for v in RL. But the point here is what will always happen is that the only vertices you'll get are lattice points. These will actually always be in L. So in fact, all of the vertices you get are in lattice points. And this is where, this step here is where unimodularity comes in. That's why you need unimodular, is just for that point. And then, get a resolution. And of course, there's some details in these steps, making sure all of them work, but this is broadly how you get it. And remember, labeling vertices is enough. Okay. I claim that, okay, some of you might have noticed, but this is actually something that you might have heard about or might have seen before in some other setting. This is actually the embedding of, this is the ideal for P, whoops, that's not a P. Okay, I was about to write the wrong thing. P2 into P2 cross P2. All right, so this is the diagonal by the diagonal. So let me just write a delta. All right, this is the ideal for that embedding. Oh, the transcription is working. I can use the transcription to tell if I have any sound. Right, and so what I actually want to say is how I want to frame the rest of the talk and how I want to frame the question that we're gonna, well, that we really want to discuss is if I have an embedding by a toric variety of a toric variety, can I resolve the ideal I get from that? Right. So let's frame that question. Let's write down that question. Where did I put my notes? There they are. This one is minimal. I guarantee this one is minimal. What do you mean? There might be a generator missing in JL. I was being sloppy. Okay, I was hoping it was a complete intersection. I wouldn't have to think about it. I was just like, it'll probably be a complete intersection. I'm probably just missing the generator for the third edge. That, yes, in fact, I know I'm missing the generator. I have to be missing the generator. So if I am resolving the right ideal, this resolution has to be minimal for the same reason that you can tell minimality about cellular resolutions from monomial ideals, which is none of the labels will divide each other. Right, none of the labels will be equal to each other. They all divide. They have to divide each other. None of them will be equal to each other. Yes. The ideal generator as it gave our correctum to torus. The meaningless statement. But yeah, in general, what I'm gonna do, the resolutions we're gonna construct today for the most part, well, yeah, the resolutions that we're gonna construct for today for the most part are in general highly non-minimal. Let me actually fix this. I feel bad about it. I can read off the last, I should be able to read off the last generator. You do need 3 generators though. So this is not over the Laurent polynomial ring. That was my non-statement of if you work over the Laurent polynomial ring, this is the generators of the ideal. But this is over the polynomial ring. But then we construct modules over in the Laurent polynomial ring viewed as a module over the polynomial ring and do things there. And so this is where it gets a little tricky because you have Laurent polynomials, but you do not have the Laurent polynomial ring. Was there a question?
In this case, I'm getting data from lattice spaces. It's like 1 minus 1, 0, 0.
I mean, this is a lattice basis too. It's just that it's not enough here because it's not in general enough to do a lattice basis. And that's why I was like, oh, well, maybe it's a complete intersection, then I don't have to worry about it. But I should have realized that one can't be. That one has to be that. I'm used to doing a slightly different variation of this, which is you can do the point into P2. It looks almost exactly the same, but that one does not technically fit into this framework, but does still work. And that one, it is enough to take 2 of them. Okay. So the big question I want to ask for toric embeddings y into x, I should do a hook. Can we give resolutions and so now part of what I'm going to do is actually I'm going to change what I mean by resolutions a little bit, and that'll help us solve the problem, because this is sort of this at least for the diagonal, this unimodular case is not quite, but almost the only case you can actually do directly using this technique. It just every other case, you're going to get non-Cohen-Macaulay things in general, and they're just not going to be length whatever the right length regardless. Or in some cases, you might get some magic happening by chance, but in general, you don't expect this to extend directly. So you have to ask what we mean by resolutions.
Can I ask first what
Yes.
X is for?
I mean x and y toric. The map is toric. Everything toric.
And you're resolving the Cox ideal. Y.
Yes, well,
Okay.
yes, but we'll get there. I want to not say that quite yet. Instead, I am going to write down a theorem. Again, not of myself, but instead, this is a more recent theorem though. Hanlon, Hicks, and Lazarev. This is 2023. That well, I don't really need it. Oh, I do need it once. Okay. I didn't know if I named it for a reason in my notes and I forgot why I named it. Let this be embedding, a toric embedding. I should maybe call it a toric inclusion. I don't know. I don't know which name I like best, but I mean, in this sense, I have a map of toric varieties that is an inclusion, right? A toric map of toric varieties. Then there exists a resolution of I just realized I hope I didn't get the star in the wrong place, but it's I don't actually like dealing with sheaves all day. Someone tell me if I got the star in the wrong place. Exist resolutions of this backwards. Bottom? Yeah, I was looking at my notes. I'm like, this looks real suspicious, but maybe I should trust my notes. Resolution of this of length. Well, technically less than or equal to, but they will get something equal. Let's say less than or equal to. No, it can't be less than or equal to. Equal, coding. Sorry. There's a less than or equal to in some other theorem in this that I'm used to talking about. So again, it's this code inbound is the, so, oh, sorry, I didn't tell you what I'm resolving, how I'm resolving it. Resolution of this of length of by, this is the wrong order of words, by direct sums of line bundles. So this is a free resolution and not a locally free resolution in particular. The sheaf side, locally free vector bundles versus line bundles. That's just the annoyance.
So line bundles.
Sorry. Did I say it backwards? Not necessarily. Sorry, locally. This is a locally free resolution, but in particular, it is a free resolution. Yes, yes, that's what I meant to say. But you don't want to think of it as a locally free resolution. It's not. I don't want to resolve it as vector bundles. It's resolving as direct sum of line bundles. Yeah, it's better than a locally free resolution. Yes, that's the point. Okay. So again, codimension, best you can get. So this is as good as you can hope for, right? You couldn't hope for anything better. And I want to point out that they were not trying to solve, well, they were trying to solve a variation of this question, but they didn't come at from a commutative algebra perspective. They came at from a mirror symmetry / algebraic geometry / symplectic geometry perspective. So this is actually the corollary that they care about is specifically for the diagonal. So there exists a resolution by line bundles of the diagonal x into x comma x for x, a toric variety. Well, a smooth, I didn't say smooth. Somewhere I need smooth. Let's say everything is smooth. You can get away with less, but you need something. Otherwise, things do break. For x, smooth toric. And this is a toric Orlov's conjecture. Well, it proves toric Orlov's conjecture. So this is what they actually cared about. Right? This is the result they wanted. This is their big theorem, is that toric Orlov's conjecture is true. If you haven't seen Orlov's conjecture, it's actually a really nice statement. It's related to some things that I care about, but it's about how complicated sort of the category of coherent sheaves are. And the way you measure how complicated is how many steps does it take to generate an object, which is morally the length of a resolution. But technically, in their setting, they're allowed to do things that aren't compatible with being an actual resolution. They can take monads, they can do summands, they can do other things that we don't really necessarily want to do in the context of syzygies and resolutions. Right? Okay. So broadly speaking, I want to say proof idea. Use mirror symmetry. Well, let me say to inspire a cell structure, a cell complex labeled by, well, really sheaved line bundles. And not a space, let's put here. So really, they are using some cellular type of resolution, but they're not using the tools that we're using here. They're reconstructing some of the tools, in fact. They rebuild some of the tools themselves. And in fact, they don't prove that it's a resolution using the techniques of cellular resolutions. They prove it's a resolution by checking on each affine patch using their complex. They're saying that my complex is simple enough that I can check on each affine patch. I am, in fact, a resolution, and so I'm a resolution as sheaves. So a priori, the resolution need not be a resolution on the side of modules. And a priori, we have no idea what module they're resolving, right? Even if it is a resolution, right? It turns out that none of us noticed that this theorem is easy. I mean, this is not the work of this paper is actually quite good. It's a very nice paper, but it turns out you can prove this at least in the smooth setting. Theirs is slightly more general than smooth. Without doing anything complicated.
Are there examples of non-smooth, like simplicial toric varieties and embeddings where it's not?
So you say stacks, and then their theorem is correct. And you say smooth stacks. So their theorem is for smooth toric stacks. And I don't want to say that for obvious reasons. But certainly smooth toric varieties is the place to start. And then simplicial stuff you can get away with because you get the smooth model as a toric stack. Non-simplicial stuff is just, it doesn't make any sense anyways. Well, the question makes sense, but a lot of the things that you would try to do just don't make sense. Yeah. So I'm going to say theorem. Brown, Ehrman. This is 2024. That theorem is true. Well, let me say it precisely. I wrote it down precisely, but then I was considering let y into x be a toric embedding. Toric embedding. Let I be the defining ideal. Then, well, the word I would, there's two ways I can phrase this. You can either say there was a virtual resolution of the right length, which is actually exactly the same as saying there's a line bundle resolution. Or you can say S mod I normalized, this is the integral closure, is Cohen-Macaulay. I want to phrase it this way because it makes the proof even more obvious. Proof by obviousness. I mean, it's not quite like you have to say a couple words, but Huxter's theorem. I gotta get the right name. Yeah, I was about to transpose the E and the T. It's not so good. Okay. That's really morally the point. There is a little bit of translation that I'm hiding by stating the theorem this way, which is, why is this now still the right sheaf? Well, I'm a smooth toric embedding, so in particular, I'm normal. So this normalization, this integral closure is normalization, and normalization does not affect any geometry. It can't touch the actual y, and so nothing has changed. You have to be a little careful, just make sure that this actually is correct. But nothing has changed as far as the sheaf is concerned. And so a resolution of this is a resolution of S mod I as far as the sheaves are concerned. And so this is brilliant. This is a much shorter proof than the paper that this was inspired by. But they were inspired by this paper. They looked at this paper and like, if this is true, the only possible thing that could be happening is this, right? But they did not prove does HHL resolve S mod I bar? I mean, it probably should, but it's not proven. And it's not entirely obvious how you resolve S mod I bar in a quick way. So that's the content of, well, that's the result of our theorem, but the content of our theorem is, it comes back to our cellular resolutions. Right.
Sorry,
Yes.
so The question is what, whether their proof resolves,
Yeah,
what is S mod I bar exactly? Is that?
it's the integral closure of S mod I, right? As an S module. So here's the main theorem. I'm slightly behind schedule, but that's fine. I just better not spell my co-author's names wrong. And I'm really out of space. And this will hopefully come out very soon. The paper has been in progress for infinitely long, but it is almost there. But this theorem has been done for a while. For L inside of Zn, there exists cellular. Whatever I mean by this is we have to define this in this context, but I'm not going to define it in this talk. Cellular free resolution of the integral closure S mod S mod I L bar of length dim L rather equal to codim of S mod. Well, I guess I should say codim of the ideal and not the quotient I sub L. So this is the result. Technically, this is not enough to answer the question, but also, moreover, the stratification of this resolution. Ooh, that's not fit of this resolution is the resolution from HHL of H on the dot, right? No minimization, no nothing. It's on the dot the thing. Of course, this resolution is not in general minimal because the resolutions that they give are not in general minimal. So you can't expect minimality in this case. They are minimal for the diagonals. In the diagonal case, they are minimal, and there are other circumstances in which they're minimal, but they're in general not minimal. The other thing I want to say is it's good that this is still on the board. I did run out of time to, well, maybe I can do it, but I don't have that much time to actually draw an example of this particular behavior. But you do the same basic idea of Weyer-Persescu-Sternfelds, but now you have to worry about this step, this unimodularity step, right? In general, it's not unimodular. And so you're going to get extra vertices, and you just have to deal with the extra vertices correctly and verify that the extra vertices, in fact, exactly give you the normalization, the integral closure. And so the answer was hiding in plain sight. Someone just had to figure out that it was there. And so this really is inspired by the techniques of Weyer-Persescu-Sternfelds and Weyer-Sternfelds. But this is the final result. And the corollary in a pithy form is HHL equals BE for the diagonal. Otherwise, they have a minimization in between. Okay. I'll stop there so that, I mean, it's 52. I think that's a good time to stop.